Assalamu alaikum. Today we are going to discuss alternative approaches to controller design. In the earlier class, we have used the pole placement topology for phase variable system represented in the phase variable form only. So if the system is represented in some other form, either cascade, parallel, okay, a controller canonical form or observer canonical form, then how can we actually apply the controller design? So this is what we are trying to do. So there is two ways of doing it. First method is same as before, making the matching the coefficients of the determinant of Si. So basically determinant of Si minus A minus Bk. Okay, so you have to find out that one. And based on that, you have to figure out the characteristic equation, one characteristic equation, and our desired characteristic equation based on the pole locations, whatever we choose, pole locations. Okay, so based on that, we have our desired characteristic equation. So from these two characteristic equation, equating the coefficients, we figure out the gain values K. So this is the design probably involved, which is same as before. But the difficulty is with other forms, apart from the phase variable form, if we try to apply this technique, then for systems with higher orders, the calculation becomes complicated. So that is why it is only limited to a system that is of order 2 or 3, but higher than that, it is not comfortable. So let's solve one problem with a second order system. Let's solve example 12.3. Okay, so ys by us is given, which is 10 by s plus 1 and s plus 2. So we are giving a specification that 15% overshoot we have to follow, as well as the settling time has to be 0.5. So we can represent the system in the cascade form, which is easier to represent. Just give the integrator with a feedback, appropriate feedback, that is -1 and -2. Then join them with a gain 1. Okay, so then your output is 10 times the constant is only the first phase variable. So basically with a gain of 10, it goes to the output. And the input goes to the second state with a gain 1. So this is your x1, and this is your x1 dot. This is your x2, and this is your x2 dot. So now based on this diagram, we can easily find out the system's state space representation. Okay, so and also if we go for the feedback now, we can easily find out the feedback with these are the additional arrangement, that is we are applying the every state has to be feedback with the corresponding gain in it. That is minus K1 minus K2. Now, can we figure out what will be the modified state equation by this diagram? So as you can see, what is our U here is nothing but R minus K1 X1 minus K2 X2. Now, which is going to add with this this X2 dot. So let's start with the X1 dot. X1 dot is basically minus 2x1 and then plus x2. and x2 dot is basically you have a gain of minus x2 as well coming. So basically minus k1 x1 minus k2 plus 1 k2 plus 1 x2 plus u. So we can represent this one in the in this format, like x dot equal to minus 2 1 minus k1 minus k2 plus 1 x plus what is our u? U is 0 1. Okay, so now what is our, and that is also because we already modified u, so it will be wrong to call it u, so definitely it will be now r. And what is our output? Output y equal to 10 0 x. Now what is our characteristic equation from this new system matrix? That is this one, from this one, which is nothing but a minus bk. So our characteristic equation will be si minus a minus bk. Okay, so that will lead us to s plus 2 minus 1. I'm just skipping one line. K1 s plus k2 plus 1. And if you further simplify, s plus 2 into s plus k2 plus 1 plus k1 and s square plus k2 plus 3s plus 2 k2 plus 2 plus k1 equal to 0. So if you represent in a more appropriate way, then the k2 plus 3 s plus k plus twice k2 plus 2 equal to 0. Now this is our characteristic equation. Now we have to figure out our system's characteristic equation, and before that we actually have to use the given values. This percentage overshoot was given as 15%. So the zeta value that we can calculate from this formula minus ln percentage overshoot by 100 divided by root over pi square plus ln square percentage overshoot by 100. So that will give us an approximate value of 0.5169. And also from the settling time, t s equal to 4 by zeta omega n, and ts is given as 0.5. So plugging the values, also you can plug the value of zeta, that will give you omega n is equal to 15.476 or 15.477 as well. So, and also you can also find zeta omega n as 4 by 0.5, that is 8. And now we can easily find out what will be our desired characteristic equation, that is s square plus twice zeta omega n s plus omega n squared. So s square plus 2 into 8 s plus omega n squared, that is 15.477 whole square. Now if we apply all this, then you're going to get s square plus 16s plus 239.5 approximately. Now you have to compare these two equations. So basically this has to be equal to 16 and this one has to be equal to 239. So k K2 plus 3 equal to 16. K2 plus 3 equal to 16. That gives us K2 equal to 13 and K1 plus 2 into K2, that is 13 plus 2 equal to 239.5. Okay, so if we subtract the values, we're going to get K1 equal to approximately 211.5. So now the gains are being evaluated. So this is what we are trying to figure out originally as well. So basically minus K1 is minus K1 is minus 211.5 and this is minus 13. So our designing is done. So this is simple because of this fact that this is just a second order system. But in some cases, the system of higher order may not be as easy as this one. So for that, we have to go for an alternative method. That is, we always want to go for the system designing in the phase variable form. So that is why whatever the system is given, say alternative forms. So from alternative forms, what we do is we change it to phase variable form. Then we do the designing. Then we revert it back to original state, original form. Okay, so this is the second technique. For that one, we need to do a bit of formulation first, then we'll go with one example. So say a system that is not represented in the phase variable form is z dot equal to az plus bu. So first thing we should do is going for the controllability check, whether the system is controllable or not. For that, we can find out CMZ equal to B, AB, A square B, and goes on to AN minus 1B. Okay, so now we want to convert this. The checking is done when the system is controllable. Once the system is controllable, what you can do is you can convert it to phase variable form. So for that, we have to have a transition matrix. So say the transition matrix is P, so we can represent Z equal to PX. So Z is alternative forms other than phase variable, alternative forms, whereas your X is the phase variable form. So now if you plug in Z into this equation, then what you're going to get is Z dot is PX dot plus AZ APX so APX plus BU. Okay, then you take the P inverse in the both sides. So X dot equal to P inverse APX plus P inverse BU. And what about our output? Output for the say we haven't mentioned in the original system. So in the original system, Y, say Y equal to your CZ. So accordingly, in the phase variable form, it will be Y equal to CPX. So Z is simply replaced by PX. So this is our phase variable now. So now let's try to figure out the relation between the controllability of phase variable and the other forms. So now, whether you have noticed or not, this is our modified A, or you can say AX, and this is your BX. Okay, so since you're only going to need those two, we can find out controllability matrix CM for phase variable CMX as modified B, which is P inverse B, then AB. So more P inverse A, P into B, that is P inverse B, then P inverse A, P whole square, then P inverse B, goes on up to P inverse A, P to the power n minus 1 B. Okay, now if we try to make it simple, what you can see is P inverse B. Here, as you can see, these two are vanished. What you have is P inverse AB. And the next one will be P inverse AP, P inverse AP, P inverse B. As you can see, these two are getting vanished. These two are getting vanished. So ultimately, which will also be continuing. So as you can see from this one, what you're going to get is P inverse B, P inverse AB, P inverse A square B, and finally P inverse A n minus 1 B. So we can take common of the P inverse, and that gives us the previous controllability matrix CMZ. So we can easily find out a relation between the two controllability matrix. And after a bit of, if you take P in the both side, because this is my matrix, so you have to be careful. So PCMX should be equal to CMZ. Now P should be equal to CMZ, CMX inverse. So this is what we are trying to do is we're trying to convert one system into another system. For that, we need controllability matrix P. So basically, this is how from two controllability matrix, we can easily find out what will be the transformation matrix. For conversion, we need the transformation matrix, not the controllability matrix. So basically, from the controllability matrix, we can easily figure out what will be our transformation matrix. Now, once and those two should give you the same result, same rank, because they represent the same system. Now, since we're trying to go for the designing in the phase variable form or in the X notation, so basically we can assume that our input U is minus KX X plus R. And if we put it into our X dot, which is we just derived P inverse A P X minus P inverse B K X X plus P inverse BR. So we can take common, and what you're going to find is P inverse, then you have AP minus P inverse B KX X plus P inverse BR. And there is no change in the output equation. Output is Y equal to CPX. Now, since this equation in the phase variable form, the zeros of the closed loop system are determined from the polynomial form, okay, from the CP. So it is, and which is how we are finding the zeros of the system, and that is already explained in the section 12.4. So you can easily figure out the output equation y equal to CPX. Now this is our equation of x dot. Now once we have our designing done, basically finding the values of kx, then we have to convert this system again back to the original form into z domain. So to finding the z, what you have to do is x. Previously we have used z equal to px. So basically what you have to use is x equal to p inverse z. So this is what you have to plug into this equation. And now if you plug it, so it will give us p inverse z, and you have dot as well, equal to p inverse a p inverse z minus p inverse b kx p inverse z plus p inverse br. Okay, as you have already noticed, these two will be cancelling each other. So you have p inverse z dot equal to p inverse a z minus p inverse b kx p inverse z plus p inverse br. If you take p in front of every one of them, multiply with p in the both side, then you're going to get z dot equal to p and p that will be cancelling each other. So az minus p and p that will be cancelling b kx p inverse z plus br. Okay, so we should have find an equation like this: z dot in original system a minus b kz z plus br. Okay, so if the k that is representing the kj, but in our case, the k is actually represented. We have designed in the phase variable form, so that is why our instead of kz we have kxp inverse. So if you know the compare this equation and this equation, you can find a relation between kx and kz. So you can say that kz should be equal to kxp inverse. And if you actually know the P matrix, and then we can easily figure out in the original system what will be the state feedback gains K. Okay, so this is how actually you have to solve it. And since they represent the same system, their transfer function has to be same as well as their corresponding characteristic equation. So this is the relevant formulation that is required to find out the system design, the system that has been represented in some other form than the phase variable form. Then we design it into convert after converting into the phase variable form after designing. Then we convert it back to the original form. Or in the mathematics, we are going to see basically we are going to convert only the gains to the original system. So very quickly, let us look at the example 12.4. Example 12.4. So we have given g of s equal to s plus 4, s plus divided by s plus 1 into s plus 2 into s plus 5. Now we can represent this one. We have to consider a percentage overshoot of 20.8% of OS, and TS is also given that we should satisfy is 4 seconds. So first thing first, let us represent the system in the cascade form. So which is easier to find. So minus 1 by s, minus 2, minus 5. Then the output can be related to first phase into 4 and the second phase into 1. So 4 and gain 1. Okay. And the middle one, joining 1, the gain 1. Then you have your input with the gain 1. And this is your output. So system is represented in the cascade. Now, can we find out the very quickly the representation? So system represented in some other form, z dot equal to basically az z plus bz u, and that is x dot. So name them very quickly. So this is your x1. So x1 dot, x2 dot, x3 dot. So x1 dot is basically minus 5x1 plus x2, and no link with x3. x2 dot equal to minus 2 and 1, and x3 dot is only linked with minus 1 with its own state variable, and the other two are 0. This is our z plus 0, 0, 1 u. Okay, so and what is our output? Output is y equal to basically, as you can see, minus 5, 1 is coming here. So at this point, it is minus 5x1 minus 5x1 plus x2. So minus 5x1 and then 4x1. So it will be minus x1. So that is why minus 1, 1, 0. Now, very quickly, what you have to do is you have to find out the controllability matrix. Method is already discussed. So B as it is 0, 0, 1, then B into A. So 0, 0, the last column will be just repeated. So 0, 1, minus 1. And then with this one, you have to multiply the A matrix. And that will give you approximately 1, minus 3, 1. Okay, so how we have figured it out based on BZ, AZ BZ, and AZ square BZ. From that one, we figured it out. Okay. Next is controllability check. So you can find out the determinant of CMZ. So if you find the determinant, we're going to find that it is minus 1. So conclusion is system is controllable. So if the system is not controllable, we stop right here. We don't apply the pole placement technique. Okay, so the next step is to find, to convert this one into our, to find out the characteristic equation based on this system matrix that has been given as A. Okay, so basically determinant of Si minus Aj. And that will give us S0, 0, 0, S0, 0, 0, S minus 5, 1, 0, 0, minus 2, 1, 0, 0, minus 1. And for the simplification, we'll give you s plus 4, 5 minus 1, 0, 0 s plus 2 minus 1, 0, 0 s plus 1. And simply s plus 5 into s plus 2 into s plus 1. And if you just do the multiplication, you're going to get s cube plus 8s squared plus 17s plus 10. So this is our characteristic equation. And as we know that the both the system is represented, they are actually same system represented in different way. So basically they will have the same characteristic equation, and only from the characteristic equation we can represent, we can easily find out what we with represented in the phase variable form. So we can easily figure it out. X dot equal to a xx plus bxu, which will be simply, we know that 0 1 0, because x1 dot is equal to x2 based on that 1 0 0 1, and then the characteristic equation in the reverse order with a negative sign, of course, minus 10 minus 17 minus 8. And this is your x plus your controllability matrix is always 0 0 1 in case of phase variable. So u, what is your output? Output is same as before, and in the phase variable form, the output equation is only dependent on the numerator, that s plus 4. So, and since there is no feedback, so s plus 4 gives us basically, and this is the constant, and this is your basically this is the coefficient of x1, and the coefficient of s is basically the coefficient of x2. So basically 4 1 0 x. And since we have this A matrix and B matrix, we can also find out CM, X, controllability matrix for the phase variable form, and that will give us 0 0 1. Then just multiply 0 0, it will give you the last column, so 0 1 minus 8. And now if you multiply with this one, the A matrix, that it will give you 1 minus 8, 47. Okay. So you have now two metrics, CMX and CMZ. So the transformation matrix P can be figured out easily with CMZ and CMX inverse matrix, and which will be approximately, according to the book, 1 0 0 5 1 0 and 10 7 1. Okay, so once you have the transformation matrix, now let us figure out the system gain. So for the gain, what we know that our a specification given is this is our percentage overshoot, and for zeta value from the same formula, then ln minus ln percentage overshoot by 100 divided by root over pi square plus ln square percentage overshoot by 100. It will give us approximately 0.447. And the settling time Ts equal to 4 equal to 4 by zeta omega n. So zeta omega n is definitely 1, and omega n you can further calculate 1 by 0.447, which is approximately 2.237. So you can find out the characteristic equation of the dominant poles, s square plus twice zeta omega n s plus omega n square should be equal to 0. So s square plus 2 into 1 into s plus 2.237 whole square is equal to 0. S square plus twice s plus 5 equal to 0. Now, since our system is a third order system, so where should be the other pole? So just a review of your the approximation of a second order system, how you do that is that if you have third pole that is far away from the second order pole, then that is good for us. We can take that assumption. So we can take a pole that is far away. But if you have a pole nearby, nearby zero, nearby zero, very close to the dominant pole, then actually there has to be cancelled by a nearby pole. So this is our second. So just review. Okay. So there is a third one, but which is not effective. So in our case, this is what you have to apply. So in our case, we have a zero that is very close to our dominant second order pole, and the location of the zero is s plus 4. So we exactly take in the same location to make it even more precise to the second order approximation. So we are assuming we have our third pole which in the same location of our zero. This is square plus 2s plus 5. So this will give us our desired characteristic equation using the pole zero cancellation. So desired characteristic equation is basically after multiplication, what you're going to get is s cube plus 6s square plus 13s plus 20. And what should be our design matrix? This is our matrix in the phase variable form. So we know that with all this, only in the last line or the last row, we have to add the gains K1, K2, K3. So that will give us a design system that is x dot equal to ax minus bx kx x, which is equal to 0, 1, 0, 0, 0, 1, then minus 10 plus k1 minus 17 plus k2 and minus 8 plus k3. And the beauty of the phase variable form is designing the phase variable form is you don't have to find out the characteristic equation. Only from the last row we can predict what should be our characteristic equation. So the characteristic equation which we should be obtaining from the determinant of Si minus Ax minus Bx Kx, which without solving we can write is that S cube plus the coefficient of this one, that is 8 plus K3. And since we have multiple domain, X domain and Z domain, so we can write X, K3X, S square plus 17 plus K2, S, K2X as well, and plus 10 plus K1, X. Okay, so coefficient. So this is 0. Now we have to compare these two equations. So if we compare these two equations, this one and this one, we can easily figure out that the value of K1X has to be equal to minus 10. Okay. Okay, so 20 equal to 10 plus K, so it will be equal to minus K2 equal to basically 10. So 20 equal to K1X plus 10, so basically plus 10. And K2X will be similarly minus 4, and K3X will be minus 2. So we have done the designing in the X variable, that is phase variable. So Kx is basically 10 minus 4 minus 2. So next what you have to do is we have to find out what is Kj. That is what you're looking for. So Kx P inverse will give us. So if you apply it, then we're going to that it is actually minus 20 10 and minus 2. So from the original system, so basically KZ1, K1Z, this is K2Z, and this is K3Z. So now if you give those and then you try to find out the system's gain with the modification that we have is, let's try to take some other ink. Okay. So this is your R with again 1, then all the state will be actually represented. We'll have a bare feedback on that one. Okay, so minus K1, that is this one will be basically minus 20. Then this one will be 10, and this will be minus 2. Okay, so this is how you have to do the designing. So the system represented in this way is also a bit complicated, but in real life, what we are going to do is we are going to solve it using any programming language, either Python, Scilab, Python-based Scilab, or in the MATLAB. So this matrix manipulation will not be that critical. So this is how we have to do the designing. So basically, the formulation that we have done, the designing is slightly more simpler than that, with the assumption that, with the fact that the system has same characteristic equations, we can easily figure out what will be its corresponding phase variable form. So this is alternative approaches to controller design, which is for systems, those are represented in some other form apart from the phase variable form. Okay, see you in the next class, inshallah.